The slow moving thermal neutron. What is the energy? I think if you look at the SU it's telling something 0.03. Very small, this one, slow moving. Look at the kinetic energy it should possess. That's why we call thermal neutron. If such a neutron, if it's captured by uranium-235, then it will disintegrate into the fragments. This barium and krypton are fragments and 3 neutrons. And what are these 3 neutrons? They are fast moving. They'll have the kinetic energy of order around, say, like a 20 megaelectron volt or something. Fast moving neutrons, that one. Neutrons generated in fission. So what is this uranium-38? It is fissionable. It can break up into, it can disintegrate only when it captures slow moving thermal neutron. There's a basic necessary condition. So what happens if neutron is of high speed? It may not capture. Even if it captures, it may undergo alpha or beta decay or some other thing. But what is our basic requirement? It should undergo disintegration. That one. So therefore, slow moving thermal neutron is what the essential. So can it undergo fission? Yes. And what is barium krypton? Barium krypton, their middle weight. I think we have done yesterday some problem. The binding energy of barium krypton is greater than that of the uranium. So therefore, energy will be released here. And per reaction, the energy will be released around 200 megaelectron volt, approximately, or 220 it will come. That will take one problem where I'll show that calculation. So this is about the basic conditions. So I think yesterday we have discussed the equations. No, here we have is showing this equation, this particular thing, and also you write a plus Q. This Q on an average you can put 200 megaelectron. Now, is it not that again this fast moving thermal neutron? This look at that are generated. No, this will be again captured by uranium-235, but it's a fast moving. I should slow it down. So how to slow it down, that one? So let's assume that some means I slowed it down. Then again the kinetic energy of this has become very small, of order 0.3, and the uranium will capture. Next time it may not split up barium krypton. I just told you. So they may test you in exams, because in books they're shown chain reaction and everywhere they're showing barium krypton. Need not. There are some 56 different types of fragments will come. These are called like a fragments or products. These products can be of 56, or some books they said 76. Altogether, I think if you look at the Singage or SU or Mono, if you gather chemistry books, easily some 30 different types of fragments will come. Barium krypton is what? The one which has become very popular in the book. In the book, they have described most of the concepts using this. That's why every book is showing that one. Not only barium krypton, it can be anything. That's why it's telling, I think rubidium. This is, I don't know symbols name. Cesium, rubidium, xenon. This, I don't know this names. Only a few familiar things what I know it. So this again, the fast moving thermal neutron, it is slowed down. Energy is released. This energy released in what form? Kinetic energy of fragments. What all the energy released will be in the form of kinetic energy of these fragments and also these neutrons. This fast moving neutron, I'll slow it down. Again, when it's captured by uranium-238, again it will break up. Middle weight. And if we go and check the binding energy of the daughter is greater than that of parent, or mass of parent will be greater than that of daughter. So energy will be released here. Again, fast moving thermal neutrons. So what are these? Strictly, they are fast moving thermal neutrons. So again, this neutron, if it captured by this uranium, it will give, say, like some fragments you can see. There, here I shown 3, no? Looking at this reaction, 2 neutrons. Again, one of the neutron captured, I slow it down, captured by uranium-235. Again, you can see 3 neutrons. It all depends upon the type of fragments. It can be 2, or sir, is it 0 neutron? I don't think so. We have any fission reaction where 0 neutron is there. And I don't prefer that, because I won't go for chain reaction. So I want a reaction. I want the situation where the neutrons should be released here. So able to get this one. So like this, what happened? So some books say, don't say these are wrong. It can happen, that one. It can happen. So like this, what happen? The neutrons are released. So now, what is our main purpose? We have to sustain the reaction. Sustain means in the sense chain reaction. Means once if I supply neutrons, on its own, what happened? The reaction, the chain reaction should take place. Again, these neutrons should be captured by uranium-235. Again, further, it should release 3. So like that, a continuous chain reaction should take place here. For this to occur, what is the basic necessity? This fast moving neutron should be slowed down. How to slow down? I'll go back to the basic collision idea. There the neutron is there. So the best thing is, there's a nuclear reactor. These are the uranium fuel rods. U2O3, uranium oxide is what main thing. In that, what happened? The 90% or so let's take 90% will be uranium 238, and only 10% is what? Uranium 235. And the uranium 235 is what needed, no? The reaction what we're discussing. Let's see that what this will do, what this will do. So therefore that black dots, what you see, no, that is uranium 235. The remaining everything is what? Uranium 238. The rest of everything. So this is a dot we are showing. So or this is uranium 235 and this is uranium 238. So what you can see that gray color, the ash color, that rod itself is uranium. In that what happened, you can see uranium 235. Why dot? Because you look at the composition, uranium 235 is what? Around the 10% of that. So somewhere here and there, I am showing few dots here. But for the reaction, what is needed? Uranium 235 is needed. Okay, done. So now first what happen? I'll send a delayed neutron. Delayed neutron means slow moving neutrons. Neutron gun, I'll switch on. So let it go and strike here. So then once the uranium 235 it captures here. So here you can say captures. It'll give 3 neutrons. These neutrons are fast moving. So I should slow down. For that, what happen? I'll go for heavy water, deuterium, and look at the neutron. And this particular neutron weapon, it's not one deuterium here. So this heavy water is filled up. The rods are immersed in heavy water. Are you getting now? This blue color is what? Heavy water. Water as coolant and moderator flows between fuel rods. This one. I'll make it to flow and circulate so that I can decrease the temperature of that one. So here what happens? This is a deuterium, no? And we know neutron deuterium what happen? We have please permit teacher to discuss concept. In the end you can ask that one. So moderator, everything will come in order. At the end of the topic you can clarify your doubts. Okay, now there's a deuterium. So this blue color is a deuterium. Now this neutron, when it goes and collides with the deuterium. So what is a deuterium? 1H2, one proton, one neutron. Okay, let's do one thing. There's a neutron. When it goes and collides with a, so can it go and give kinetic energy to this? There's a kinetic energy of neutron. There's a deuterium which will be at rest. Just since you know collision, it'll be very much easier. So when it goes and collides, so what will happen? There'll be transfer of energy. Then sir, after collision, this will become K1. The deuterium, what will happen? How much it will be? I think I'll write K2. So definitely I can say K1 less than Kn, kinetic energy of neutron. So like that, not one collision. Again, this will go and collide with some other deuterium. So it's continuously, no, it will pass through it. Please try to analyze here. So everything is a deuterium heavy water. So millions of deuterium nucleus will be there, no? Or deuterium atoms, better you can call heavy water. This is that one. So like this what happened? Due to series of collision of by the neutron with the deuterium nucleus. So what happens? Its kinetic energy keeps on decreases, and finally, its kinetic energy. The arrows are showing 1 collision, 2 collision, 3 collision, 4 collision. Like this, 5, 6 collisions. What will happen? Its energy will become very less. It'll go and strike now the uranium 235. Here is what? Uranium 235. It will capture. Uranium 235 will capture. It will disintegrate into fragments. Again, 3 neutrons will come. Fine, 3 neutrons will come. Again, these 3 neutrons, again this neutron, high kinetic energy as it collides series of collisions. So it will become again now very less kinetic energy. And once kinetic energy become less, then when it goes and strikes uranium 235, again like this, the chain reaction will take place here. Moderator means one which will decrease the kinetic energy. Moderator moderates. Please moderate yourself. We'll say please control. So here what will happen? We will control the kinetic energy of deuteriums. This particular thing. So you can't place one molecule here. Am I right? I think you can't place one deuterium because what type of neutron we want? Neutron with very less kinetic energy. So therefore, it should undergo some 5-6 collisions on an average. So it should undergo collisions till kinetic energy becomes very small, of order 0.02 kilo or mega electron volt you put, very small that one. So for that, because of that, what will happen? The deuterium is used. The deuterium is called as a moderator. Water is coolant and moderator. So what is a moderator now? Like a one that decreases kinetic energy of fast moving neutrons. And what is a good moderator? It's a deuterium. Heavy water, enriched heavy water. You take ordinary water, no, it will have less proportion of deuterium. So I'll enrich it so that the quantity around 40 or 60% of deuterium is there in the water. No, that particular thing is what I'll fill up here. Okay, agree this. Okay, this is the thing. Now, I want to control the reaction. Means I want to control. So to control that, what happen? Okay, to control that, what happen? The neutron should be controlled. No. So how to what to bring? Now I'll prefer a control rods. So this is called like the blue color are called as the pink color control rods. So what they do? They'll just absorb the photons, so neutrons here. That one. So what are the usually control rods made up of? Boron. So I'll put one small reaction. Now we know this is a neutron. When it encounters a boron, this one, what do we get? We get lithium 37 plus alpha particle. So what happened? The neutrons. Totally what happened? They are they'll got converted, no? So when this fast moving neutron, what happens again? When they go and collide with the boron, no, this reaction occurs here. We'll get lithium 7 and alpha helium plus. Also like a helium nucleus, will get it, or alpha particle. So like that, what happen if I want to decrease the neutrons? Because see, once say I'm just showing few millions of like this uranium 212, there millions of neutrons will be there injected. Then what happen? I should know how to control the fission reaction by just controlling the number of neutrons. Suppose there are 1,000 are there. I want to make it only 100 neutrons. Then what happen? If I push the control rods more into this one like this, if I push it more deep here, then what will do? They'll absorb more neutrons will come and strike. And if I take it out totally, this pink color, I'll totally take it out here. Then what happen? More neutrons will come and strike the uranium 235. So like this, by moving this control rod up and down, means up and down, I can control the number of neutrons striking the uranium 235 or number of neutrons available in the nuclear reactor. So these are called as a control rods. What they're made up of? Boron. So these are some very popular things: boron, cadmium. What are the control rods? What is the duty of control rod? They absorb. There's a property of that particular element. They absorb neutrons. Example: boron, cadmium. So these are the they will absorb neutron. There's one property. There's a chemical property of that. Instead of this heavy water, no, we go for some graphite. But since heavy water is much very easy to fill up, no, so usually you can say in the books also they say like heavy water, deuterium. That's one. So what is a moderator? Moderator made up of deuterium nucleus. Deuterium, that one. Enriched water enriched by deuterium. So like this, what happen? I can now what I can do? I can control the rate of reaction, how much of energy should be generated, and what is that energy, where it is available. I'm not seeing energy. Means now the barium krypton which are there, no, they are made to strike the one metal. Clear this. Then when that barium krypton goes and strike the metal, the kinetic energy of that barium krypton, you can say copper. It's a good conductor of it. No? So when this barium krypton, they come with kinetic energy, like this millions will come. When they come and collide with this, the kinetic energy will be converted into heat. And here what happened, I'll pass a water, that one. So let this be warm water. Here we'll get very hot water. Or you can say better steam, hot steam. This steam, what happen, I'll make it to rotate turbine. And you know that one, there's a big wheel where a magnetic field will be present. And as it rotates, what happen, electricity will be generated, that I'll transfer it. So here is what the left hand side, what nuclear reactor. What all that kinetic energy of the fragments, the fast moving fragments, when they come and strike that big metal plate is not something, it should be very big enough, that one. So usually it will be of around 150, around you can say 100 meters, like that. The side length, square plate, this one. So when it comes, a lot of heat will be generated. And this particular thing, what happened, the heat generated, what happened, again, these are made up of copper. Copper is a good conductor of heat. The water which is there here, the water which is flowing here, the water which is flowing here will become hot, or it will become steam. And that steam, what happened, will go in with a high temperature, no, the steam will be blown, and that steam will rotate the turbine, and as the turbine rotates in a magnetic field, EMF will be generated. This is the thing. So the left hand side is what, the nuclear. Here the reaction occurs here. Okay, got this? So that energy is not some sort of heat. The energy which is released in the reaction will be in the form of kinetic energy of fragments. Got the idea? So these are about very good theoretical questions they may ask you, like control rods. They absorb neutrons. Why they one that decreases the kinetic energy of fast moving neutron, that is the deuterium. That's called like a moderator. Let's come for the fuel rod. What is the fuel rod made up of? There's a chain reaction. Is it okay? And need not be always barium krypton. I just shown, go through it. And again, you look at the Singh or SURMA. There are some other 8 combinations are there. Just have an idea. You'll be in better position. So when you're writing this equation, what should be the charge and the number of nucleons must be conserved. And what all that energy is, how we have to calculate. If they give mass of parent minus mass of daughter. If they give binding energy of daughter minus binding energy of parent. Like that, we'll calculate the Q. Okay, let's come for that one. If you look at the uranium, the biggest problem what we are facing. The uranium rod, the fuel rods, uranium-238. What happens uranium-238? It's also radioactive, no? Is it also fissionable? Yes, it's a fissionable, but it's not a fissile. So here we are bringing the word fissile and fissionable. So what do you mean by that? Means uranium-235, will it not capture the neutrons? Will it not capture the neutrons? Uranium-238 also will what happen, capture the neutrons, but it cannot sustain the chain reaction. That's the major problem with the uranium-238. I'll come to the focus on now the uranium-238, because the fuel rod is made up of uranium-238 and uranium-235. So what is this? This is a fissile and fissionable. Means it will break up into 2 middleweight fragments. What about this? This is fissionable but not fissile. What do you mean with it? Means it cannot, uranium-238 cannot sustain chain reaction. Why it cannot sustain chain reaction? What is the problem with that? No, for uranium-238, for it to undergo fission, means suppose say, let's give that one, uranium-238 nucleus. If it captures neutron, what should be the kinetic energy of this neutron? Should be of greater than around 1.4 mega electron volt only. If it is greater than 1.4 mega electron, then uranium-238 will capture. Then it will undergo fission. So can you give guarantee that the neutrons which are emitted will have this much of energy? Need not know. Go back here. So these neutrons which are emitted, can you ensure that they will have this much of kinetic energy? Need not. The kinetic energy of neutrons will not be how much around, say maybe one neutron, this will have 3. The other one will not have that even 1.4. So these neutrons open, every neutron cannot have that much of the kinetic energy around say more than 1.5 megaelectron. So therefore this what happens, though this particular neutrons which are generated, their kinetic energy will not be sufficient to go and being captured by uranium-238 can capture only those neutrons whose kinetic energy will be more than 1.4 megaelectron volt. And it will undergo fission. And again, in turn, the uranium-238 which will generate, no, this will be suppose by chance, okay, I'll put it, cannot sustain chain reaction. This one next again put it as uranium-38 is fissionable when it captures neutrons of kinetic energy more than 1.4. Some books they said 1.2, some books they made 1.8. On an average, I'm taking it. More than 1.4. Fissionable, I'm putting that one, fissionable. Okay, somehow we'll see that 1.4 megaelectron is available. Then again, when the uranium-238 undergoes fission, what it generates, the neutrons, their kinetic energy will be less than 1 megaelectron volt. It's a fissionable, but not fissile. Are you able to understand? So no. Okay, next point we'll write. That's the first thing. Next one. When uranium-238 undergoes fission, it generates neutrons of kinetic energy less than 1 megaelectron. I think there's a big problem, no? Can we accelerate neutron? What is a neutron? A charge, not a charged particle, no? And it's very difficult to accelerate that particular neutron. Of course, sir, why don't you bring neutron gun? Inside a nuclear reactor, I cannot bring neutron gun. Okay, from external neutron gun is there, I can project some neutrons. So for it to undergo chain reaction from uranium-238, what it generates neutrons, they should only initiate further reaction. So therefore, this is the biggest problem what we have with the uranium-238. And I think in the this sentence are very important. More than one options. Fissionable but not fissile. The reason is this particular thing. Okay, agree this. So there's a one regarding uranium-238. So what happens if uranium-238 captures uranium-238 captures a neutron? What conditions will arise? Now we have a breeder reactors, it is called as. When uranium-238 captures the neutron with this one, so it will become uranium-239. This is another problem. It need not undergo much fission. So instead of undergoing fission, so what will happen is it will undergo beta decay. It will eject an electron, beta emission, beta minus. You know what is the half-life? Half-life is 23 minutes. The moment it captures the neutron, fast-moving neutron. Sir, you said fast-moving neutron captures undergo fission. It's all probability. So instead of undergoing fission, what happened? The uranium-239. So what happened after 23 minutes? Within 23 minutes, after 23 minutes, what will happen? It will undergo the beta emission. After beta emission, what happened? It will become neptunium. 239. Then the Neptunium what happen will undergo further beta emission. So what is the off-life? Off-life will be around 3 days. After 3 days, after beta emission, what will happen? After 3 days, it will undergo beta again, one more beta minus decay after 3 days, and this will become plutonium. You see this. So here what happens, there's a very good, this is what we use for weapons. And this plutonium as radioactive, I can use for in the nuclear reactor. Okay, it's not there our syllabus, just I'm giving this basic idea. This is what happens. So uranium-238, though it captures the fast-moving neutron, it need not undergo the fission. It may undergo a beta decay like this. It all depends on the probability here. Again, they'll create a conditions where what happens, let it not undergo fission, we'll get a plutonium. Plutonium is what we use in the weapons. This called like a breeder reactors here. So what all we use, the bombs, no atom bombs, we go for plutonium only. Because what is the reason? Because uranium-238 constitutes what? Almost 90% of uranium ore. So what I do is in the nuclear reactor, once what happened, the uranium-235, when I use it completely, what is left over? The uranium-238, no, that uranium-238 what happened? So what do we get after the end of that particular, like a fuel, uranium-235, when I go and check it, no, I'll obtain the uranium plutonium. And this plutonium is what I'll use for the to make atomic bombs. So that's why we are not getting the uranium fuel very easily. If somebody supplies you uranium fuel, what happen? What you should do? You should supply back that plutonium. You should return back. But most of the countries, they don't return. What they do, they'll make this atom bomb. That's why nobody will supply the uranium fuel like that only. So what is the biggest problem with the nuclear reactor? The fuel is the problem. So what is the 1 kg of uranium? Anybody? Uranium ore. What is the 1 kg of it?
42.
Yesterday, I think that's no, around 50,000. Very enriched, maybe 1 lakh rupees. It's very cheap, but not available. You don't get that easily. So what you do if you have reactor, the end product of reactor, what you get? You get a plutonium. And this is what widely used in the weapons. So that's why if you construct a nuclear reactor, you don't get fuel. If you get a fuel, what happen? The end product what happen will be used for plutonium, will be used for weapon. That's why the International Regulatory Board what happen will not permit you to construct reactors that easily. Even if you construct, then they don't give fuel. So there are a lot of constraints are there. There's one basic idea of the uranium-238. They may ask you this particular data if it captures. These are the half-lives. This is okay. Let's get into the nuclear reactor again. Okay, let's see that what is the in a nuclear reactor fission is produced in 1 gram for in